Welcome to the webinar series presented by the International Adsorption Society. The IAS is an international organization dedicated to advancing adsorption as a solution to scientific, engineering, and human welfare challenges through the promotion of adsorption research and education. We hope that all of our attendees, their families, and their colleagues are safe amid the ongoing COVID pandemic. We thank everyone for attending the webinar today. The webinar series began in the spring of 2020 and then restarted last autumn, and it has had an immense success, and the recordings of these webinars continue to be viewed on YouTube. We plan to continue these webinars through the present academic year with a variety of speakers from industry, academia, and other research institutes, as well as PhD students and early career researchers. Subsequent webinars will be announced on the IAS mailing list and the IAS Twitter feed. Today's webinar will be presented by Dr. Conchi Ania from CNRS, France. I'm Arvind Rajendran, a professor at the University of Alberta, and today's webinar will be moderated by Nick Wilkins, who is a graduate student here at the University of Alberta. We are required to remind attendees and future viewers that the views expressed by the speaker, host, or other moderators are not necessarily those of the IAS or the institutions associated with those individuals. We ask that you consider joining the IAS as a regular member if you're not already one. Our dues are minimal, only $20 US per year, but support the publication of our flagship journal, Adsorption, contribute to travel grants and workshop seed funding for IAS members and affiliated groups, as well as aid the organization of our triennial conference on the fundamentals of adsorption. Members also receive free access to IAS-supported materials, including our journal, as well as the adsorption database published by Springer Materials. Anyone can follow IAS on Twitter at @AdSauce for future updates regarding IAS events, webinars, and information about scientific meetings. Please expand our YouTube channel by subscribing. The International Conference on the Fundamentals of Adsorption is a premier conference in the field of liquid and gas adsorption, attended by the world's leading scientists and engineers from academia, government, and industry. The 14th edition will be held in Broomfield, Colorado, in the US between the 22nd and 27th of May, that is in about a year, and do visit the website to learn more. Now I will hand over the proceedings to Nick Wilkins to introduce our speaker.
Everyone, our speaker today is Dr. Conchi Ania. Dr. Ania is a research director at CNRS France and heads the NAFMAT research group. She received her PhD in chemistry from the University of Oviedo, Spain, and took postdoc stays at the City University of New York and the CNRS in France. She's the recipient of the L'Oreal UNESCO Research Fellowship for Women in Science, Excellence Research Award from the University of Granada, and an ERC grantee since 2016. She is an editor of the Carbon Journal and has published over 150 papers and 2 patents. Her research interests are in nanoporous materials for applications in energy storage and conversion, environmental remediation, water treatment, and gas adsorption. During the webinar, questions can be submitted to the speaker, one through the Q&A tab of Zoom, or as comments as YouTube. Those comments will then be taken to the Zoom where this is being hosted. We will take some questions halfway through the talk and then the rest at the end of the talk. And without further ado, I'll ask Dr. Ania to start her presentation.
Thank you very much. I'm gonna try to share my screen. Do you see my screen?
Yep.
Yes, okay, so we can get started. So thank you very much, Nick, for the introduction, and good afternoon, everyone. I also hope that you are all keeping safe in this current pandemic situation. And before we start, I'd like to say that I'm happy to participate in this initiative of the IAS, because I think that precisely with this current situation, at least we have, they are providing us with a channel for promoting the discussion on adsorption, which is a topic that we all share. So today my talk will be on adsorption from solution, from aqueous solution, with the specific focus on the removal of emerging pollutants, organic compounds from water for wastewater treatment. And it will cover from fundamentals for data interpretation to some examples illustrating the applications of adsorption to different case studies. This talk has been prepared to reach different audiences from young researchers which are new to the fields to those who are starting their master or PhD already working in environmental applications of adsorption. And as I've mentioned before, with this particular focus on wastewater remediation and with the use of activated carbon adsorption, but also for those researchers that work in materials development and who might be interested in the different applications of the materials that they are synthesizing. The scope of the presentation will be divided into different parts. The first one is devoted to revisiting some fundamentals of liquid phase adsorption, going from the most common theories, applies, and models. Also some words about the experimental setup for data acquisition and the interpretation, and also some tips and comments on which are the common errors or in how to avoid them during the experimental manipulation. And the second part, which will be devoted to these examples with the case studies on the industrial application of adsorption for wastewater remediation. The main objective of this talk is to provide you with some general concepts on the application of liquid phase adsorption, and not to go into deep details of the different theories that are currently used for the application of this process. An important also objective is to give you an important, at least from my point of view, list of literature, of pertinent literature in this topic, which is what I have included in here, with some titles on monographies devoted to adsorption technology, the design of adsorbers, and the application of for aqueous phase and wastewater treatment. You will also see some references to scientific papers all over the talk in the presentations, which I have found interesting for illustrating the examples that I have chosen. So allow me to start with the obvious reminder, which is the concept of adsorption, because I think it is important to put it in the perspective of liquid phase adsorption, which, as opposed to most of well-known gas phase applications, it is usually a much more complex situation or system. Because they at the liquid phase, it's usually a multi-component solution where we have a solvent and either one or two components which we want to adsorb to retain in the surface of the adsorbent. And it makes that there is, in some cases, an important competitive effect between all these different species which are in the system. So as we find it in many different textbooks, a general definition of adsorption can be considered as an enrichment of different chemical species from a fluid phase, which in this context is necessarily a liquid, on the surface of an adsorbent, which is in this context also is a solid with a more or less porosity. Just a few words to mention that examples of liquid phase adsorption are found in many industrial applications. I have included in here some sketches of most processes where particularly adsorption on liquid phase is used. And it is worth mentioning that they, for the particular case of activated carbon, the application for water remediation in either drinking water or wastewater treatment accounts for over 70% of the share of the total market production of activated carbon. It is a phenomena that has been known for many years. I mean, this ability of certain solids to retain in their surface dissolved species of water. And despite of that, it still has a lot of references with a lot of studies going on in order to optimize and to improve the efficiency of the adsorption. So in water treatment, even though the adsorption has proved to be very efficient, as I've mentioned before, it is necessary to keep in mind that the liquid phase is a mixture, at least a binary mixture of the solvent and the species that we want to remove. And the adsorbent is a solid where there is a competitive adsorption and desorption at the equilibrium from these two different species. From a thermodynamic point of view, adsorption is usually described by means of the equilibrium adsorption isotherms, which is as a function that accounts for the dependence between the amount of the adsorbent retained on the surface of our solid with the concentration in the concentration in a solution, but of course will be also dependent on the different parameters such as temperature, pressure, pH, and so forth. It's also important to consider that it is essentially a superficial phenomena, so that this change in the concentration is related to the changes between the interactions of the at the surface level, which can be very often expressed in terms of the this surface tension between the adsorbed phase, the adsorbate and the solid, and the adsorbate in the solution. Also, the most usual way to represent the amount adsorbed, which is also known as the loading, is in terms of the amount retained on the surface per unit surface area. Although for practical application, very often we also have these loading expressed as the amount adsorbed, either moles or milligrams per mass of the adsorbent, because of the accuracy, which is much higher for the determination of the mass than for the determination of the surface area of most adsorbents. What is important to consider is that the adsorption process is usually described by either the equilibrium of adsorption, which is this dependence between the amount adsorbed and the concentration remaining in the solution, and the adsorption kinetics, which accounts for the rate of the process and therefore accounts for the distribution of the adsorbed phase and the distribution of the amount in solution with as a function of the time. These two factors are important to predict the behavior of different adsorption systems and also to predict the dynamics. And the adsorption equilibrium isotherms are the basis of most of the theoretical models that are described or used to describe the adsorption process. With this idea in mind, from a general point of view, in the case of a liquid phase adsorption, most of the adsorption isotherms are classified according to the classification proposed by Giles and co-workers in his paper in 1960 in the Journal of Chemical Society. This classification of the isotherms is based on the shape of the isotherms when they are plotted, when we plot the amount adsorbed versus the equilibrium concentration. There is 4 main types of adsorption according to this type, to this shape. The first and most widely known is the L-type isotherm, which corresponds to a sharp increase in the amount adsorbed at low coverage, at low concentrations in the solution, which indicates that there is a high affinity between the adsorbate and the adsorbent. And it's very often also accompanied by the formation of a saturation plateau, which is defined by the maximum adsorption capacity of solid. The S-type isotherm, as opposed to the L-type, is indicating that there is a much lower affinity between the adsorbent, the solid, and the adsorbate, because the amount adsorbed starts to be important as the concentration in solution starts to grow. And this is also indicating that the interactions between the molecules which are in solution and the interactions of the molecules which are already retained in the surface are important to hold the adsorbed layer together inside the in the surface of the adsorbent. The H-type isotherms are a particular case of the L-type isotherms, where there is extremely high affinity between the molecules retained and the solid, the surface of the solid, as we can see by this steep vertical adsorption. And finally, the fourth type, which is the C isotherm, that corresponds to a linear dependence on the amount adsorbed with the equilibrium concentration. And it also, it is characteristic of system where we can consider this linear dependence as a constant partitioning, and is usually due to the observed in systems where there is a low affinity in between a low amount adsorbed between the of the adsorbate in the surface of the adsorbent. According to this Gilles classification, these four types of adsorption can also be subclassified in different subgroups, depending also on the common issues of the shapes. So, for instance, the subgroup number 1 corresponds to those isotherms where the adsorption has not reached the complete saturation or the formation of the first layer, as we can see in these sketches, well, as opposed to the subgroup 2, where we have a well-defined plateau corresponding to this first step of the saturation of the adsorbent. On the other hand, in the case of subgroups 3 and subgroups 4, we have a phenomena which is very commonly observed in the liquid phase application, which is the appearance of multi-layers, either in a complete form, as in the case of a subgroup 4, or in a partial form, where we can observe that it's started to be initiated the second layer, but still not reaching the saturation plateau in the case of the subgroup number 3. And finally, also there is another subgroup which is column X from maximum, which is characterized by the appearance of a maximum of adsorption, followed by an inflection point and then a decrease in the adsorption. This is characteristics of system where we have very strong solid-solid interactions, and such a particularity of the maximum followed by a minimum or a decrease in the adsorption is usually appearing when the solid concentration, the concentration in the equilibrium concentration in solution is higher than the critical micelle concentration. This paper also describes not only the classification, which is most usually applied for these systems, but also illustrates a few examples of different systems where we can find the types of adsorption isotherms described. I have introduced some of them here in the sketch, where you can see, for instance, that the adsorption of organic aromatic compounds and also some dyes and different adsorbents follow typically L, and they correspond to subgroup number 2, whereas the formation of a multi-layer adsorption is also characteristic of the adsorption of aromatics, either on adsorbents with extremely well-defined adsorption sites, or when we have also the complex systems where there is a high concentration of ions in the solution. Once the adsorption isotherms have been classified, it is important to describe them by a mathematical model. Unfortunately, due to the wide variety of different types of isotherms, up to now there is no universal equation that is capable of describing this variety of isotherms. And the fact is that there is many different equations that have been proposed all over the years in the literature. Some of them are based in thermodynamical considerations, and others are based on empirical. However, what is important, regardless the origin of the theory or of the equation, is how well this model is able to feed and to reproduce or predict, ideally, the adsorption behavior that we are studying. Among the different isotherms or models, most widely known are, of course, the Langmuir and the Flonich equation. So the first one It has a thermodynamic basis, and you can have the equation in here. It's a two-parameter equations where the amount absorbed and the equilibrium concentration depends on the factor Qm that it's considered as the maximum adsorption capacity at the saturation, and the parameter B, which accounts for a certain measure of the interactions, of the strength of the interactions between the adsorbent and the adsorbate. This equation is based on assuming that the maximum adsorption capacity is this monolayer coverage. It also assumes that there is a constant energy for the adsorption side, so it fails to predict the heterogeneity in the adsorbents. Despite of this, its popularity is due to the fact that it's a very simple equation that has a very simple analytical solution, because it can be easily linearized. There are different forms of delinearization of this equation. I have included in here the two which are most widely used, and you can see the representation for one of them, that the reciprocal of 1 over QE and the reciprocal over the equilibrium concentration should give a straight line where we can compute from the analysis of the slope and the intercept these two parameters of the equation. In a similar way, the Freundlich equation, also proposed in the early 90s, it's an empirical expression in this time where the equilibrium concentration is correlated with an exponential function of the equilibrium, the concentration in the solution. As opposed to Langmuir, it is not able to predict the formation of the monolayers, so the saturation conditions. This is one of the main limitations of this equation, that fails to predict the behavior usually obtained at high loadings. On the other hand, it provides a useful information by the analysis of the exponent n that indicates the presence of surface heterogeneity, which is not considered in Langmuir equation, and can also indicate how favorable or non-favorable is the adsorption process. I'd like to draw your attention to the fact that there are different formulations of this Freundlich equation in the literature, so we can find this equation or either the same where the exponent is the reciprocal of n. So it is important in order to consider the interpretation of the exponent, which has been the formulation of the equation used. And in these sketches in here, in these figures, I'm showing the representation of the different possibilities that we can have when we vary the exponent n and also the constant of these equations. So as we can see in here, for instance, for a given constant value, the shape of the isotherm is controlled by the value of the n exponents, indicating that low values of the n exponents indicate a favorable adsorption, but also that we have an homogeneous distribution of adsorption sites, as we can see here in this shape of the isotherms. As long as the n exponent increases, we have an open structure, which means that the adsorption sites do not necessarily have the same adsorption energy. On the other hand, for the analysis of the comparison of different adsorption isotherms, if for a given value of the exponent n, we can have that the higher value of the k values are indicating the extent of the adsorption. So that even if this parameter cannot be considered like a maximum adsorption capacity, it can be used to compare or to predict a higher extent of adsorption for high values of this parameter. There's many others models that have also been used to describe the equilibrium adsorption isotherms, and I've just selected in here perhaps those which in my opinion are those widely used in the literature. So this, of course, the Langmuir-Freundlich equation, that is, it's a kind of combination of the other two equations that introduces a new parameter. So it's a 3-parameter equation where the n exponent in here accounts for this possibility to have different heterogeneity in the solid. Also, the Rutledge-Peterson equation, which relies on the same principle as this one, and but they differ in the mode where the heterogeneity or this n exponent is applied to the equation. Also, the Dubinin-Raduskevich equation that you might be familiar with because of its extensive application in a gas phase for the determination of pore volumes. The extension of this equation to liquid phase has been proposed to be by simple modification of the relative pressure by the magnitude Cs over C, where C is the equilibrium concentration in solution, and Cs represents the maximum solubility of the adsorbent in the solvent. In this case of the Dubinin-Raduskevich equation, it's interesting to point out that the loading, the amount adsorbed at the equilibrium, has to be expressed as a molar loading in moles per gram in order to match the units that correspond to the different parameters that are holding the equation. Also, in the liquid phase extensions, very frequently, the beta parameter accounting for the affinity of the adsorbent for the adsorbent is not considered due to the difficulty of evaluating this parameter in liquid phase solutions. There is another equation that I'd like to mention, which is the BET equation that is widely used also in gas phase for the evaluation of the surface areas. It has been also extended to the application of a liquid phase, and even though it still has most of the limitations of the original BET equation, it has an advantage over the others, which is the fact that it considers the formation of different layers of adsorbent retained on the adsorbent, which is a common phenomena when it comes to adsorption from liquid phase. For those who are interested in the application of the BET equation extended to liquid phase, I would invite you to read this paper published in Adsorption in 2009, where the authors do an analysis of the different formulations for the BET equation applied to different systems in liquid phase. I'm just showing you in here the two different formulations. One is the most simple equation where the relative pressure, the term of the relative pressure in the applied in the gas phase is replaced by this value of the concentration over the concentration for the solubility, and the most generalized expression is has been developed considering that there is two different adsorption constants, one for the first layer of adsorbent, which is in contact with the solid, and the other for the upper layers where there is adsorbent-adsorbent interaction. So the authors concluded that even though the second form of the equation is perhaps most widely used, again, because the analytical solution is very straightforward, it should be more appropriate to have a better description of the systems if they first equation, the generalized equation considering the different adsorption constant is considered. Here I am illustrating with an example of the fitting of the experimental adsorption isotherms of pharmaceutical compounds from aqueous solution. There's two different examples in order to illustrate the adequateness of the application of the different equations. So in the first example, you can see that the experimental points are indicated by the symbols, and they fit into the Freundlich, and the two different linearization of the Lambert equations are represented by these green and gray lines. What I like to mention in this example is that very often when we read all the reports in the literature, we found the table with computing all the values regarding the constant of the fitting constant, the fitting parameters of these equations, and very often the correlation coefficient, but they plotting of the full fitting in terms of the experimental values and the calculated values is not very often shown in those papers. It is something very important because in most of the cases, they fitting, evaluating the goodness of the fitting by simply considering the correlating coefficient is not a good practice because the correlation coefficient is not very sensitive to all the experimental data that we might have. This is what you can see, for instance, in the case of the two different linearization of the Lammer equation, where we have a pretty acceptable coefficient, R2 coefficients for both linearizations, but we have different values for the maximum adsorption capacity, which are derived from the fact that the second linearization in this case is not able to describe very accurately the data. If we include the analysis of the fitting by some other statistical or mathematical coefficients, such as the chi-square in this case, we can see that we have, this is a much more sensitive parameter to evaluate the goodness of the fitting. And this is something that should be done with care when fitting the experimental data to different models. The same conclusions can be inferred from this second example, where the main difference is that we have experimental data going to very high values of equilibrium concentrations, which are, for instance, one of the limitations where the Freundlich equation is not able to fit the experimental data. Again, in this case, we see very high correlation coefficients, R2 parameters, and when we analyze the fitting by the chi-square parameter, we see that there is a much better description of the data if we apply either the LF or the DR models to the experimental data, something that we see also if we plot the data and the calculated isotherms. As I've mentioned at the beginning, the liquid phase, and particularly in aqueous phase, one of the particularities is that very often we have multi-component system, which can get very complex when we have different adsorbents. And also because of the solvent, then can also compete with the different adsorption sites of the adsorbent. So for this reason, there has been a lot of models also proposed for the description of the adsorption isotherms in multi-solute models. I'm just plotting in here some of the most widely used in the literature, and also with some references where you can find either the derivation of the equations or some other alternatives in order to solve the limitations. Of course, the simple extended Lammer and extended Freundlich approaches have been proposed, which are basically considering that the distribution of the different adsorbents in the solid phase are affected by the molar ratio of the other component. And this is very often expressed in a very simple way in these equations. So even though these equations are still used and are able to reproduce some of the experimental data, their main limitation is that they are restricted to have systems where the two adsorbents have similar maximum adsorption capacities from the single adsorption component, and or also when they assume that we have a similar shape in the isotherms as in the case of the Freundlich approximation. So this is not always the case, and for this reason, some propositions have been published for the modification of these extended models. I am showing you here just some of two examples proposed for the incorporation of the correction parameters or factors in the second equations, which account for the incorporation of a surface heterogeneity and also the incorporation of the interactions between the adsorbed molecules in the liquid phase. In this case, these equations can be very useful to get information about the mechanism of adsorption and also to get information about how the different adsorbates are interacting and how this is affecting the final uptake of both compounds. But the problem is that they are limited to describe the competitive adsorption under equilibrium, but they're not able to predict which is the adsorption capacity when we have different mixtures. One example of the application of these equations is given in here for the adsorption of two pharmaceutical compounds, sulfamethoxazole and metronidazole, where I'm representing the experimental uptake versus the predicted uptake. The empty symbols correspond to the applications of the bisolute number, where we can see that in the case of metronidazole, we have an overestimation of about 30% of the adsorption capacity, whereas in the case of the sulfamethoxazole, we have 82 underestimation of the adsorption capacity. So in order to predict or to match the experimental values with these predictions, we must modify the Langmuir equation. And in this case, we have incorporated the correction parameters. This is the data corresponding to the solid symbols, where we have a good agreement between the experimental data and the expectations. And this is indicating that in the case of the sulfamethoxazole, we need at least a parameter of a factor of 6, and in the case of the metronidazole, we need a factor of 1.3, which is again indicating that the competitive adsorption of metronidazole and sulfamethoxazole is affecting in a greater extension the retention or the uptake of the second component of sulfamethoxazole, where we can see that this is mainly displaced and the effect of the competitive adsorption is in favor of the retention of metronidazole. On the other hand, what is important is to get models that are able to predict this adsorption behavior. And in this case, among the different theories that have been developed, of course, the ideal adsorbed solution theory, it takes a dominant position among them all because it is able to predict this multi-solid adsorption capacity of different adsorbents based on the data from the single component solution. This theory was developed for gas phase in 1965. This is the original paper by Myers and Prosnett, and it was later extended by Radke and Prosnett also in 1972 to liquid phase. And even though it is based on some simple assumptions, such as the fact that they both the liquid and the adsorbed phases show an ideal behavior, and that there are no interactions between the different adsorbed molecules, for instance, and again that all the sites of adsorption are equal in measure. It's able to the main advantage, as I've mentioned before, is that it is able to predict they quite accurately in some cases the multi-component solutions without the need to carry out those time-consuming experiments. This is useful, for instance, when we are in a step where we want to screen the different adsorbents in order to identify which are those which might be more adequate for a given process. The main disadvantage, on the other hand, is that the analytical solution is not straightforward. We need to have a numerical approximation for computing the solution of the ideal solution theory, and also from the fact that the absorbed phase very typically in liquid phase deviates from the ideal behavior. So in order to solve or counteract this limitation, there has been also some other models or modifications to the IAS theory. Two of them more commonly used for liquid phase applications are the heterogeneous ideal adsorbed solution theory and the real adsorbed solution theory, which are based on the incorporation in the first case of energy distribution. So to account for the fact that the adsorbent can have different adsorption sites for the different molecules to be retained. And in the case of the real of the RAST, it is also considering the non-ideal behavior of the solutions by the incorporation of the activity coefficients. With these modifications, the predictions can improve for some systems, but one of the disadvantages that still remains for the applications of the IAST theory for liquid phase is that it fails to predict the competitive adsorption of different organic pollutants in the presence of natural organic matter, which, as you know, is a typical component of real water systems. The reason for this is because of the impossibility to determine accurately the composition and the concentration of the natural organic matter, which is one of the premises of the IAST theory. And in order to also to counteract this limitation, there's there's a few models. I've mentioned here two of them that propose to modify the IAST theory by introducing some corrective parameters. In the case of the tracer model, they correct the isotherm parameters of the pollutants, whereas in the case of the EBCM, the correction is done in the mathematical descriptions of the natural organic matter adsorption. In either case, they after the modifications, the competitive adsorption can be much accurately described. This is what you can see here for the tracer model and the initial IAST prediction without this correction, although it loses the capacity to predict since it requires input data of a multi-component solution. And the last part of this this first aspect on the fundamentals of adsorption, I'd like to mention some ideas about the adsorption kinetics, which is also one of the very important when evaluating or studying the adsorption process. It is important to mention that for the progress of the adsorption on a given system, it goes through different steps. I have summarized in here 4 of the main steps. The first one is a transport of the adsorbed from the bulk solution towards the boundary layer, which is formed surrounding every particle of the adsorbent. Then we have the mass transfer through this boundary layer, and which is called the external mass transfer or a film diffusion. And once the adsorbent reaches the surface of the adsorbent, and we have the intraparticle diffusions where the adsorbate can proceed. The intraparticle diffusion that can proceed either through pore diffusions or to surface diffusions in 2 different steps. And finally, we have the adsorption. Since the mass transfer from the bulk solution to the boundary layer and the adsorption are usually very fast, the kinetics of adsorption are very often defined by either the external mass transfer, which is through this boundary layer, or the intraparticle diffusions either in the pore or in the internal surface. The equation for the approximations, the equations to define the mass transfer for all these diffusion systems can be derived from the Fick equation. However, again, the analytical solution for most of these set of equations is not straightforward, and it involves the determination of different diffusion coefficients, and which is the reason why for many cases in the literature we can find different simple models, and the main ones are indicated in these, which are applied to describing the adsorption kinetic, the experimental data, which may not provide a deep characterization of the mass transfer with the knowledge of the different diffusion parameters, but they can at least give an indication of which is the adsorption mechanism or the dominant process that is governing the overall adsorption rate. Among the different parameters, if you're interested in comparing the application of these different equations, I would suggest you to read this review published in Adsorption in 2021 by Stefano Brandani, which is a nice comparison applied to liquid phase. And I would just like to mention very briefly two important aspects when fitting the adsorption kinetic data. The first one is that, again, as in the case that I've mentioned for the adsorption isotherms, we should not rely only on the R2 coefficient, correlation coefficients, because this may lead to incorrect interpretations of the goodness of the fitting. Besides the correlation coefficients, if we plot the full uptake plots, which is experimental data versus the theoretical curves, we can have a much better approximation of the goodness of the fitting of the different equations. Also, it is important to define which is the range in which these equations can be applied. And this is what I'm illustrating here for the application of the first order equation to a set of experimental data, as you can see in here, where there is a very sharp adsorption rate and a very long equilibrium of adsorption. In this case, the pseudo first order equation cannot be applied to all the set of the experimental data, and it can only be applied to the initial points where we have this gradient of concentration right before the equilibrium has been reached. So with this, that is taking me longer than I expected, I have finished with my first part of the presentation, and I'll be ready to take any questions if there is.
Okay, so we do have one question so far from the YouTube. I'll just post a notification to ask for some more there. This is from Luis Aguilera on slide 4. For the case of the MX isotherm, can the
Yes.
solute interaction effect, can that occur in the presence of only one adsorbate? And then a follow-up to that question, is it possible to reach a saturation loading at a much higher concentration than what you've seen on the bottom row of this matrix here?
I'm not sure I understood the first part of the question. Can you repeat it?
Yes. So, so in the MX case, the bottom row of that
Yes.
the matrix, can the solute interaction effect, can it occur in the presence of only a single adsorbate, or do you have to have multiple adsorbates for this effect to be possible?
Yes, it does not necessarily need to have a different adsorbate. So in fact, this is very common when we have adsorption on a polymer of surfactants, which are very prone to have to create micelles. So what is important is to have the aggregation, if the aggregation of the adsorbents in the solution. If the aggregation can be just from one adsorbent from itself, or if you have a multi-component solution, it can also be due to the interactions of different adsorbents, but it's not necessarily the case. This is just when you have such micelles, or you reach a concentration where the affinity of the molecules to be retained is much higher if they move to the solution to form those micelles than when they are retained in the adsorbent, in the solid of in the surface of the solid.
Great, and just the follow-up to that, is it possible then to hit a saturation loading or plateau at some very high concentration for this, or will you always see this this behavior where it comes up and then drops in loading?
If it is possible to have a saturation plateau, but in that case, it's below the first maximum that you have observed, because the condition to have this is that you have a whatever type of isotherm in the adsorption, you have a maximum adsorption capacity, but as long as you are increasing the concentration, then the driving force is no longer the interaction of the adsorbate for the solid, but the adsorbed molecules will actually desorb, will be displaced to go through the solution, so you have a lower adsorption capacity. So your plateau can actually be lower than the maximum that you have observed when these aggregation or micelles were not formed.
Great. We just got one other question in the Zoom. In the kinetics, the most recent slide that you've talked about, will there be any possibility of having a hybrid model?
Yes, of course. There is many different possibilities, and this is why I've included in here. And I really recommend this a nice paper by Stefano, published very recently in 2021. There is a lot of models, even the Lamware and also the Lamware extended also applied to the description of the adsorption kinetics. And the thing is that the popularity of these models that I've included in here is just based on the fact that they are easily computed and they can give information or preliminary information about the mechanism of adsorption without the need to compute the full models and the evaluation of the diffusion coefficients in the pores or in the film diffusions or in the boundary layer, which is a much more complex calculations. But yes, there is, of course, many different models. I've just introduced in here those who are more popular, at least from my point of view, in the literature.
A couple more have just come in. This one's from YouTube. Kasim Al-Nadaf. Is it possible to determine the selectivity for multiple adsorbates in a mixture, so multi-component selectivity?
Yeah, I guess that the multi-component selectivity, the question goes in a direction as compared to what we usually do in a gas phase. In this case, I think that the rather than selectivity, if I go back to a few slides in here, it's we can define the selectivity as the amount adsorbed under the equilibrium once we have these multi-solid components. So if the selectivity is defined as in a similar case, we can have that ratio. It's just a ratio of the amount absorbed considering the molar fraction of each component. So yes, it is possible.
Okay, we'll just take one last question from, this one's from a person in Zoom, Chip Kilduff. The first part's a comment and then it follows with a question. So they say, it's easy to avoid linearization and determine parameters using something like Solver and Excel to do nonlinear fitting. This avoids specific data weighting that is characteristic of many linear forms. But it also raises the question, is it necessary to weight the data? And if so, what is the best approach?
What is the best approach? I would say that the best approach is the one that fits with the experimental data. And by fitting the experimental data, what I'm meaning is that even though the assumptions or the from where the model has been created might not have a strong thermodynamic basis. I mean, we can also have the application of empirical equations. I think it is important to realize whether if the parameters that we are getting with the fitting of the experimental data, they are meaningful or not, considering actually which is the experimental data. So yeah, unfortunately, the fact that we have linearization, which are accessible to everyone because they can be computed in an Excel file or in origin very easily. This is a reality, and this is something that we have seen that everybody is using. The problem is not using those simple approaches. I think the problem is when the interpretation of the data is made based on the wrong assumptions and is made based on, for instance, just computing the goodness of the fitting based on only one parameter without really looking at whether if the fitting and the parameters that we are getting make sense with the real experiment. This is indeed extremely important and something that I have tried to explain in here because we don't see in many cases the representation of the full uptake plots. We simply have in most cases this table where we have the constant parameters and the R2 coefficient. So it is important to see the RT coefficient. The correlation might give you just an average of the statistics of your fitting, which does not necessarily mean that you are describing correctly your problem or your kinetics. So I think it is important to do whatever methods you can, and the most important part is to go back to the experimental data and to verify whether if it makes sense or not to apply that model.
Okay, so we do have more questions, but we'll wait till the end of the talk now, and we'll send the rest of them to you then.
Okay. How much time should I have for the for the?
I would say maybe about 20 minutes or so.
Okay, because it took me longer than I expected. I'm sorry about that. Okay,
No,
so
please.
but I do have a lot of information, but I think I will focus on the things that are important in my opinion, that to be the message that I want to pass. So okay, I don't know why I can. You can see my screen, right?
Yep, we can. Yep.
Okay, okay. So for the second part, but I don't know if you are. Yes, okay, now you're seeing everything.
Yeah, we are able to see.
Do you also see this bar for sharing screen? And
No.
okay, so it's just me because it was in the middle of the screen, sorry. So practical aspects of the adsorption, determination of the kinetics, and also determination of the adsorption isotherms, which I think are important. So the kinetics is well, it's basically the first experiment that we carry out, because in order to define the equilibrium adsorption isotherm, we need to know which is the time for equilibration. This is commonly 99% of the cases is done in batch experiments, which is basically putting in contact the amount of carbon or an adsorbent with the volume of the solution of a given concentration. This can also be done in column studies, of course, and in that case, the concentration of the volume of the solution is pumped through a column of small dimensions, usually in a recirculating mode, so that we can very easily attain the equilibrium. So it is important, however, to have in mind different tiny little things that can change the fact that we are having reliable or accurate experimental data or not. The first one is that it is important to have a representative adsorbent sample. It seems to be obvious, but it's actually not, because in many cases, there's many people weighing a very small amount of the adsorbent, which if it has a marked heterogeneity, it might not be representative of the whole of the adsorbent, so the reproducibility of the experiments may be compromised. Also, we have to consider which is the accuracy of the mass determination. So we must minimize the mass error. Of course, the sample has to be washed and dry to avoid concentration errors and also errors coming from the dried mass. If possible, to keep the investigator until use. Also, to be aware of which are the analytical errors in the determination of the concentration. And in the case we're using different volumes of the adsorbate, it is important to consider whether the adsorbate has a very high volatility or not, because there should be an equilibrium between the volume in the dead volume of the flask, which might also contribute to non-reproducibility data in the experiment. And another important thing that it's unfortunately commonly see in the papers is that the batch experiments have to be well planned so that the equilibrium concentration at the end of the kinetic experiment cannot be close to zero. So, or in other words, the removal efficiency cannot be close to 100%, because in that case, we would be considering that the equilibrium is reached, and in fact, we are just accounting for the full removal of the components without knowing if there is a true equilibrium or not. Another remark that I'd like to mention is that we must be careful with a particle size damage. For that, we can have a different configuration on the steering, either with the use of a canister or different steering rates. And also, we must be sure that the equilibrium has been truly attained, which is unfortunately not the case in many cases. This is an example, what you can see here for the adsorption of a chlorofluoric acid in an activated carbon, where we have the typical C/0 evolution concentration and over time. And it seems, if according to this, that after 2.5 hours, we have reach the steady state, so we are far from a C versus 0 close to 0, so we could conclude that the adsorption equilibrium has already been reached. However, if we extend the experiment for a longer time, this is the same experiment, so this is the points corresponding to these experiments up to 5 hours are up to here. We see that at much longer times, we still have a very marked decrease in the adsorption, indicating that the kinetics for this particular system was much longer than the 5 hours time that we were considering at the beginning. So unfortunately, we have to overestimate the time required for the equilibrium in order to be sure that we are attaining the true equilibrium, because otherwise all the determination of the adsorption isotherms and so forth might be affected by that. Another important example is related with this formation of these, what I've mentioned before, the negative adsorption due to the formation of critical or the formation of micelles, or which is commonly observed by a decrease in the adsorption isotherm in this case, or in some other cases when we have this increase, which could be associated to the formation of a secondary layer. Even though the two possibilities exist, the formation of the secondary layer and also this decrease corresponding to the MX type of adsorbents, in most of the cases, these are not real events, and these can be affected by some errors associated in the first case to the concentration issues, or also to the errors associated to the mass during determination of the adsorption kinetics. So in order to determine whether if we really have these two different rare cases of adsorption behaviors, we should be performing more experiments to verify by changing the loading of the adsorbent and also the initial concentrations and the volume in order to verify that we are actually having the phenomena that we are describing, and to discriminate any errors coming from the determination of the concentration or the mass. Once we know the experimental time needed for the equilibrium, so we need to build the equilibrium association isotherms, which is very straightforward if we do this simple mass balance, considering the mass, the volume, and the initial and the final concentration after the equilibrium. What is important is that when we have this kinetic data, and I have included here data, so that if you want, you can plot the data yourself. This corresponds to the kinetic of the system, where we have the evolution of the initial concentration until we reach the equilibrium. And this is also the evolution of the amount adsorbed versus the time. So if we assume that after 15-60 minutes, the equilibrium has been reached, then we just plot the two green columns, the equilibrium concentration versus the amount adsorbed, and we have what it's called like the operating lines, given the evolution of the concentration versus the amount adsorbed for a kinetic experiment. So the end of the operating line will give us a point in the adsorption isotherms, and if we repeat this step at different loadings, or even changing the adsorbent dose or the adsorbent concentration volume or initial concentrations, then we will have the different points that constitute our adsorption isotherm. And it's important to consider the operating lines, because the slope of the operating line can be very useful if we want to analyze or to design adsorption system based on batch adsorbers. This is an example, for instance, comparing two different materials with two different isotherms, as you can see, where we have the same initial concentration, and we have applied for this same initial concentrations, we have determined which is the amount in the equilibrium for a given final equilibrium concentration. In this case, the slope of the operating line is giving us also this information about the final equilibrium concentration. In the case of a batch adsorber, but in this case carried out in two different stages, the operating lines will also give us information on which is the adsorbent demand that we need to apply in the different stages. Although the usual application in water treatment is for one step in batch adsorbents, the fact is that the applications of two different steps, consecutive steps, can be very useful in order to increase the amount adsorbed or to decrease the amount of adsorbent that we need to reach a final concentration. This is what I have illustrated in here. For instance, for the system, if we follow this simple mass balance, where the total mass is the process is the mass of the two different steps, which is computed also by the initial concentrations and the amount absorbed, which is information coming from the isotherm. If you take the isotherm, in this case, for an initial concentration of 1 ppm of a pollutant, and for a final desired concentration of 0.1 ppm, we can very easily compute this dependence of the total dose with the amount of the adsorbent in the first stage. And we can see that we reach a minimum amount of adsorbent needed to have this initial, this desired final concentration. So that in this case, we can save almost 20% of the adsorbent by using a two-step batch adsorbent. Adsorption can also be carried out, of course, in a batch in fixed bed, and this is the most useful application of in water treatment of granular activated carbon, as opposed to batch absorbers, which are typically applied for powder activated carbons. So in this case, what is important to consider is that there is main difference between the amount absorbed if we compare the batch adsorber from the equilibrium adsorption in a fixed bed. The fact that in the column in a fixed bed, we have a continuous feed of the initial concentration. So the adsorption takes place. We have a zone of the column where we have the complete saturation of the carbon. So that the adsorbent is in equilibrium with the initial concentration. We have the mass transfer zone where the active zone, the active adsorption is occurring, and then a fraction of the adsorbent which is fresh or not used. However, since this we have this continuous feed of the initial concentration, very often they operating line that is defining the amount absorbed in a fixed bed is has a much higher slope than in the case of the batch adsorbers, so that the equilibrium concentration that we can reach under these conditions is higher than in the batch absorber. Of course, this is the ideal situation if we consider that the breakthrough curve has an ideal shape, which is very vertical, and also in practice, the achievable loading at with this column is not only marked by the maximum adsorption capacity under equilibrium conditions, but it's also marked by the maximum permissible levels of the pollutants, so that in reality several columns can be used. For the principles for the operation of a fixed bed absorber are similar for those in gas phase, and for those who are interested in this topic, I invite you to review the webinars presented by Professor Morgenstern and Professor Farouk in April and May last year, where they describe the design and interpretation of breakthrough experiment, either in gas phase and in liquid phase. And so my purpose here is just to show you some of the important parameters that we need to know in order to design these fixed bed absorbers, which is the total stoichiometric capacity, which is corresponding to this shaded area in this plot, which corresponds to the total time before the exhaustion of the bed, and also to the time of the used time, or the time equivalent to the usable capacity, which is coming from the integration of this of the numerical integration of the data at the breakthrough point. This will also give us information about which is the fraction of the column which is used or not used, which is also very important for the practical applications of a fixed bed absorbent. So considering this, I'd like to share with you also some of the real case applications using activated carbons for the removal of different compounds. So the reason for this is that, well, we all know that in the case of adsorption, any chemical can be removed from water. It's just a matter of increasing the amount of the adsorbent. However, the question to be asked is whether if its benefits are worth the impact. Is it effective to increase? Is it economically attractive? And this is why we need to perform a screening of the adsorbents, which can be or must be optimized depending on the quality of the water and the composition of the water. So starting from some general ideas, the first message that I like to pass is that in real systems, there is the systems are really very complex. So there is no straightforward correlation between the uptake of different molecules to be retained and the characteristics of the adsorbates, because it really depends on many different parameters at the same time, either the molecular weight of the adsorbent, the concentration, the dynamic diameter, polarity, and regarding the activated carbon of the adsorbent, also the surface chemistry, the surface area, the pore size distribution. So there is a whole package of different parameters that are affecting the amount adsorbed. And this is the reason why we need to do these screening experiments in order to find the optimum adsorption capacities. So in this plot, what I'm showing you here is just a series of uptake for different carbons, which characteristics are not important right now, or the uptakes corresponding to different pharmaceutical compounds that you have computed in here. So the important thing is that we can see that for a given carbon, the affinity towards the different pharmaceutical compounds, the variability of this affinity is dramatic, because we can have uptakes going from almost 400 milligrams per gram to less than 50 milligrams per gram. And for a given pollutant, we can also have, in the case of sulfamethoxazole, for instance, we have a pretty good acceptable capacity in this case of this carbon, and a much lower capacity in this case of the QOX, which is just the slight modification of the carbon upon oxidation. So it is really important to consider all the different factors that we can have regarding the composition of the water, but also regarding the composition of the adsorbent. So since among them, of course, the porosity and the surface chemistry, which are also very important, then I'd like to move forward to, but I would still leave you these slides, since the talk is being recorded, so perhaps you can get useful information, even if I don't have time to describe them. I would like to move to a real case operation, a case study in a wastewater treatment plant in Germany that we carried out a few years ago, where they different pilot scale plants were investigated for the removal of a few pharmaceutical compounds. So we have 4 different modules which incorporate, as you can see in here, either granular activated carbon columns or powdered carbon in a membrane filtration. Another module with a combination of powdered carbon in a membrane bioreactor, or in modules C and D, which incorporate the combination of ozonation with powder activated carbon adsorption, and finally adsorption mixed with the flocculation system. So all these different pilot scales modules were tested for the removal of these compounds and their degradation metabolites, which were found at the exit of the effluent in this particular wastewater treatment plant in Germany. What we can see in here, for instance, if we compare the pilot scale based on the biological activated sludge and combining the granular activated carbon columns with the powder activated carbon in membranes, we can see that you can have also here the legend for the concentrations of the effluent the effluent before the advanced treatment and after the treatments of adsorption with the different carbons. We can see in here that after the powder activated carbon, we still have a concentration of these compounds, which is non-negligible, whereas the adsorption in the columns in this case gave us the absolutely complete removal for these compounds. Similar performance were obtained for the other modules, the one with the ozonation performing much better than the others, which is what you can see in here. This is the removal efficiency of the modules before the utilization of the different processes based on adsorption coupled with other techniques, where the maximum removal efficiencies were no higher than 40 or 45%. However, when we combine with granular activated carbon columns, we have efficiencies higher than 90%. And also in the case of the combination with the ozonations, we have very high efficiencies for the removal of the different compounds, indicating that in this case, the coupling of adsorption with advanced methods, it's an adequate treatment for the pollution of these water treatment plants. Another project that we are working on right now is the coupling of these different modular technologies also based on adsorption, coupled with photocatalysis on the demonstration sites in Israel and in Spain, with the particularity that the water to be treated has different challenges. In the case of Israel, we have a very high salinity, and in the case of the wastewater treatment plant situated in Spain, we have an increased organic matter and also concentrations of emerging pollutants. In this case, we have a pretty good removal efficiency also when they modular technologies, the adsorption is coupled with photocatalysis. This is what I'm showing you here for different pollutants. Unfortunately, I cannot give you information on the nature of the pollutants that are being treated. This is the just the adsorption capacity in the dark, and this is what we have when we couple the adsorption with the UV utilizing photocatalysis systems, which also has the advantages that we have during the adsorption, we not only degrade the adsorbent which is in the solution, but we are also contributing to the self photoassistance for regeneration of a adsorbent. So in this case, also another advantages of using the carbon is that we are also improving the ecotoxicity of the treated effluents, which is not always the case when we are applying photocatalytic treatments. And I'm with this, I'm finished because I'm too over the time. However, I would like to give you here some adsorption examples, which are kind of exercises with this solution, where you can see how the application of the equilibrium adsorption isotherms can be used for the design of different adsorption systems, either in in a batch absorber or in a column. So since you can perhaps review this during the YouTube channel, you can also try to solve these adsorption examples yourself and to match with the solutions that is given in red, which is basically different situation. This example, the third one, it's corresponding to what I've explained before about the advantages of using one stage of a two-stage slurry absorbent, where you can have here also the equation and you can compute all the data. And also some indications on what kind of information you can extract for the design of adsorption filters, designing the useful capacity, and also the flow rates, and also the most adequate column diameter and the dimensions of the column in the case of real cases for the decontamination of pollutants. So with this, I will be glad to take any further questions, and I really apologize for the time. I went over much over the time I was planning at the beginning.
Thank you for the great talk, Dr. Ania. We do have a couple questions, some that we didn't get to during the The break, I'll start with that one. This one's from YouTube and Gitana Dures. Is it possible to model and measure adsorption at very low concentrations, for example, at the parts per million or parts per billion scale?
To model and to measure? Yes, it is possible. It is much more complicated when we have the ppb scale than the ppm, but it's also what is happening in the real life. So because of all those examples that I was mentioning for the presence of pharmaceutical compounds in real wastewater, the actual concentrations are usually of a few ppbs. It's very rarely that emergent pollutants, they reach the ppm scale, because you have to consider also that usually there is already, adsorption is applied as a end of pipe solution, meaning that we have some other treatments already applied to the treatment of the water before adsorption takes place. So even if the concentration of these pollutants were in the ppm level, when it reaches the adsorption capacity, we have already ppb level and a very low. So the complexity of these systems is not to compute or to model once you have the experimental data, is to actually detect accurately the concentration. So it's the analytical detection that poses a problem rather than the adsorption process itself.
This is a question from Chip Kilduff on Zoom. When using adsorption as a polishing step after wastewater treatment plant, is pretreatment or filtration needed to avoid fouling of the adsorbents? And then just a side, he thanks you for the talk and thanks you for talking about some of the very important considerations.
Okay, so yes, if you're going to use a torsion in a column system, in a fixed bed adsorbent, you need to eliminate the the natural organic matter or the suspended solids that you have. So the water has to be as clean as possible, other than for the dissolution of the compounds that you want to remove. However, you have to consider that in the case of wastewater treatment, this is already, in most cases, the case, because you have different filtration systems in the plant, and then you have typically the activated sludge, and then the water, after being coming out from the reactor, the biological treatment is directed to. Maybe I can go back to. Yes. In here, for instance, you see, this is the typical configuration where you would have the application of the granular activated carbons, or even a batch reactor. So all the filtration steps that you need are typically already incorporated in the previous steps of the water treatment. However, if this is not the case, you do have to include a pre-filtering step before you enter the columns for the granular activated carbon. Usually it's sand filters would just do the job.
Okay, one more from YouTube. This is from Luis Aguilera. If the equilibrium is reached very fast in a batch system, let's say less than 5 minutes or so, with which variables can we do a kinetic study? So I think he's talking about which type of models you'll be able to fit if you have a very fast kinetics.
The problem, if you have a very fast adsorption kinetics, and I'm coming to here, is that you most probably would have not many experimental points in that part. So either you have an automatized experimental setup so that you can have many points during those 5 minutes, or you would have, in the best of the cases, you would have like 4 or 5 points. And under those circumstances, unless of course you are doing the adsorption kinetics in a recirculating system with a column. So unless you have enough experimental points, I would not do a kinetic treatment, because you would be just trying to fit not enough information, and all the information that you could have from the fitting might not be accurate to describe the system. However, if you do have the enough data, because you are in, as I said before, one of these columns where you can have the automatized data recording, then there is no limit for any of these models. I mean, in this case, it is most likely that the external film diffusion, this contribution, this diffusion through the boundary layer is going to be very fast. And what you should be seeing most likely is the intraparticle diffusion inside the porosity, the tortuosity of the adsorbent. So I would say that you would have to focus more in the intraparticle diffusion, but at least, again, it will depend on whether if the model fits to the experimental data that you have.
Excellent. I think, Nick, we don't have any further questions.
I'm not seeing anything else in the Zoom or the YouTube, at least.
Okay, if Conchi, if I may just take over the screen sharing to just conclude.
Yes.
Okay. So thank you very much, Conchi, for this wonderful presentation and also taking the efforts to put in some examples. I'm sure particularly our students would really benefit from this. So we hope the viewers also enjoyed this presentation. And we look forward to having this on YouTube as soon as possible. The next talk is scheduled for June 14th, and this would be by Professor Yoshi Kawajiri from Nagoya University. And he's going to be talking about Bayesian approaches for adsorption, isotherm, and process modeling. Do follow up with the IAS mailing list and our Twitter pages to know the exact time of this talk. So once again, we thank you for attending today's talk, and we look forward to seeing you in another webinar. Thank you, and have a good weekend.